Welcome to The Explainer. Today, we're unraveling a pretty fascinating engineering mystery that's literally hiding right inside your home. I mean, have you ever stopped to wonder why some of your everyday appliances seem like absolute geniuses, while others, well, act like they don't have a clue what's going on around them? We're going to explore the amazing evolution of control systems, basically looking at how machines went from operating completely blind to becoming incredibly self-aware. Okay, think about this for a second. It's super relatable. Why does your air conditioner know exactly when the room is perfect and automatically shuts off? But your toaster will happily just sit there and burn your bread to an absolute crisp if you set the dial too high. It kind of seems like just a funny quirk of household chores, but the answer actually lies in a fundamental difference between two incredible types of automation. And that difference? That's exactly what we're going to unpack today. Section 1. The era of blind machines. When appliances just don't listen. All right, let's dive right into this by first looking at what we call blind machines. These are systems with absolutely zero environmental awareness. They are programmed to do a job, and they will stubbornly do that job no matter what is happening around them. We call this open-loop control. It's a system where the control action is completely independent of the output. Simply put, you give it an input command, and the machine performs the operation without ever checking to see if it actually achieved the result you wanted. There is no feedback mechanism here to automatically correct errors or deal with disturbances. It just blindly does what it was told at the very start. And you know what? You use these systems all the time. Take that electric toaster. The heating process operates for a preset time, totally ignoring the actual color or temperature of your bread. Then you've got washing machines with fixed timers. They run the exact same cycle whether your clothes are just slightly dusty or absolutely covered in mud. Traffic lights on a simple preset timer are open loop, stubbornly changing colors even if the street is completely empty. And that simple electric fan in your room? Same thing. You set the speed and it just spins, regardless of how freezing cold or blazing hot the room gets. Section 2. Inside open loop control, a one-way street. So let's look under the hood at the actual engineering to see why they behave this way. Notice how the information flows in this rigid, straight line. It's a literal one-way street. An input gets fed into the controller. Then the controller pushes a control signal directly into the controlled process, which leads to the final output. That's it. The flow of information only goes from left to right. Once that signal passes the controller, there is absolutely no looking back. Let's apply that architecture to a really practical example. An older automatic clothes dryer that uses a simple timer. On the input side, you've got the desired time you set on the dial. The controller is just the timer itself, pulling in electrical energy. That timer tells the heating elements to fire up, creating heat for the clothes, which is our process, and that hopefully results in dry clothes at the output. But notice there are no arrows pointing backward. The system doesn't actually measure the dryness of the clothes. It's really just a sequence of dominoes falling forward. But here's the fatal flaw in this whole linear setup. Let's imagine a worst-case scenario. Halfway through your cycle, the dryer door accidentally pops open, and all that heat just escapes. What happens? Well, because it's an open-loop system, the timer just keeps counting down regardless. It blindly runs for the full 30 minutes you initially set. And at the end of the process, you're left with cold, wet clothes, because zero information was fed back to the machine to tell it, hey, we lost heat, pause the cycle. Section 3. Sensors, the missing link. So how do we fix this? How do we cure these blind machines and finally give them some awareness of their surroundings? Well, the solution is sensors. In modern mechatronics, which is this awesome blend of mechanical, electronic, control, and computer engineering, sensors act as the literal sense organs of the machine. Just like you use your skin to feel if something is hot or cold, machines use sensors to detect physical parameters. They monitor things like temperature, pressure, displacement, and humidity, and then they convert those physical realities into electrical signals. Without these sense organs, the operation stays entirely blind. Section 4. Inside closed-loop control. The power of feedback. Armed with these powerful sense organs, engineers created a massive breakthrough that allows machines to adapt, correct themselves, and essentially think. We call this closed-loop control. In this type of system, the output is continuously monitored and then compared directly with the desired input value. If there's any difference between what you want and what's actually happening, the system generates what we call an error signal. And that error signal, it's used to automatically adjust the operation. It's basically a smart system that is constantly double-checking its own work. Let's walk through the logical steps of how information routes through this much smarter setup. First, you set an input reference, basically what you want the machine to achieve. Second, the controller amplifies the signal and kicks off the controlled process, just like before. But here is where the real magic happens. Step 4, sensor feedback. A sensor monitors the output and sends that data backward. This unlocks Step 5, error correction. The machine calculates the exact difference, the required result minus the actual result, and actively adjusts itself to shrink that error down to absolute zero. Okay, let's revisit our clothes dryer example. But this time, let's make it a smart dryer. Notice that new path swooping backward in the updated design? The sensor is deriving a feedback signal directly from the actual dryness of the clothes. If your clothes are still damp, it creates an error signal, and the controller will pump up the temperature or extend the time. On the flip side, if the clothes are basically dry, the controller can dial back the heat or just stop early so it doesn't ruin your favorite shirt. It handles those random, everyday disturbances completely effortlessly. Section 5. The right loop for you. Now that we've got a solid grasp on the deep mechanics of both systems, let's take a step back and compare them. The visual contrast here is really striking. On one side, you've got that rigid, one-way, open-loop system. But on the other, simply adding that feedback path literally bends that straight line into a continuous, intelligent circle. The entire closed-loop configuration is completely characterized by this feedback signal. The machine is essentially having a constant, real-time conversation with itself. Now, you might be wondering, if closed loops are so smart, why don't we just use them for everything? Well, it really comes down to cost and complexity. Open-loop systems are incredibly simple. They're economical, and they're super easy to design. If high accuracy isn't a huge deal, they are fantastic, even if they get easily thrown off by external disturbances. Closed-loop systems, on the other hand, are highly accurate, reliable, and incredibly stable because they're always self-correcting. But that precision comes at a price. They're significantly more complex to engineer and a lot more expensive to build. But when precision is an absolute must, closed loops are literally everywhere. And this brings us right back to that hook from the beginning of our explainer. Your air conditioner uses a closed loop with a thermostat to stop cooling the exact second your room hits that perfect temperature. The cruise control in your car is constantly monitoring your speed against hills and wind resistance, adjusting the throttle completely automatically. From automatic water level controllers in big industrial tanks, all the way to those highly precise robotic arms on manufacturing floors, closed loops are the absolute backbone of modern smart technology. And I think that perfectly illustrates this profound journey from simple, stubborn timers to incredibly intelligent, self-correcting machines. By integrating sensors, we close the loop, completely changing what our machines are capable of achieving. Which leaves us with this final, kind of provocative thought. If sensors are truly these sense organs of mechatronics, what entirely new senses are we going to give our everyday appliances next? Thank you so much for joining me on this explainer. And hey, I hope you never look at your toaster the same way again.